atomic design is changing how electronics are built. A shift is underway in how electronic materials are conceived and produced. Instead of refining performance after fabrication, new research points to a model where functionality is designed directly into materials at the atomic scale. A collaboration between the University of Birmingham, the University of Warwick, and European research partners has demonstrated a method for constructing atomically precise nanoribbons with programmable electronic characteristics. Detailed in Nature Communications, the study highlights an emerging pathway for developing materials suited to flexible electronics, compact connected devices, and next-generation computing systems. Rather than modifying established materials such as graphene, the team focused on building entirely new molecular structures. The approach reflects a broader move toward embedding electronic behavior into the architecture of materials themselves, though significant barriers remain in scaling these techniques beyond laboratory environments. Programming electronic behavior at the molecular level. The research centers on donor-acceptor chemistry, a framework commonly used in polymer science. By arranging electron-donating and electron-accepting molecules in defined sequences, the researchers were able to control how electrons move through the resulting nanostructures. This method alters the traditional materials development workflow. Instead of relying on post-processing steps or chemical modification after synthesis, electronic properties are determined during the design phase. Adjusting the sequence and length of molecular building blocks allows for precise tuning of conductivity and electronic response. Potential applications extend across multiple sectors. Materials engineered in this way could support lightweight and flexible electronic systems, including wearables and embedded sensors. There are also implications for improving energy conversion in solar technologies, as well as enabling more compact architectures for IoT devices. In healthcare, similar design principles could inform the development of bioelectronic interfaces used in diagnostics or implantable systems. Bridging lab-scale synthesis and industrial application. The nanoribbons were synthesized by depositing specially designed molecules onto a gold substrate under vacuum conditions. When heated, the molecules shed bromine atoms and self-assembled into linear chains. Depending on their arrangement, the resulting structures form donor-only, acceptor-only, or hybrid configurations. Using advanced microscopy techniques, the team was able to observe these structures at atomic resolution. This allowed researchers to directly correlate molecular arrangement with electronic performance, an area that has historically been difficult to validate at this scale. The findings showed clear and consistent relationships. Extended donor sequences enhanced electron donating behavior, while longer acceptor chains increased electron affinity. Hybrid structures introduced more complex electronic responses, influenced by the precise ordering of molecular units. Despite these advances, challenges remain in translating the process into scalable manufacturing. The reliance on vacuum environments and metallic substrates presents limitations for integration into existing semiconductor production. Moving from controlled synthesis to commercially viable fabrication will require further development. Even so, the trajectory is becoming clearer. Materials science is increasingly focused on designing electronic functionality at the atomic level, rather than adapting it after production. For industries working in advanced electronics, energy systems, and connected devices, this signals a longer-term shift toward materials engineered with precision from the outset.